Hey folks, we're finishing up our notes here from the tangent line problem. Or about the tangent line problem, which is basically the idea of the derivative for the first time. So we talked a little bit about continuity and differentiability and how they fit together. We're going to come back to this again. So if you left these notes kind of confused, we'll come back to those in a minute. But I want to talk a little bit about what does it look like to be differentiable? Like we know what it looks like to be continuous. The left side limit and the right side limit have to reach at the same height. I mean, they don't have to, it can be two totally different functions, but as long as the y values are the same, then we consider that function to be continuous. When we talk about differentiability, what we want to talk about is this phrase locally linear. A function that is differentiable at a point is said to be locally linear. That means that if you zoom in real close to the curve at that point, the graph looks more and more and more like a tangent line. It looks more and more and more like a line. So if I don't have that scenario as I zoom in near an x value, then my function is not going to be continuous at that, not continuous, is not going to be differentiable at that location. So what we're going to do here is we're going to take a look at some functions, and we're going to try to determine if they are locally linear at the indicated point. So we're allowed to use our calculator. Now, we'll talk about it after. Well, actually, no, let's try this first. Pop quiz, make a sketch. Sketch the graph of e to the 5x. Hopefully, you drew this. And the point that we expect you to know here is the height of 1. That's the point 0 at a height of 1, because e to the 0th, when I put 0 in for x, that becomes 0. E to the 0 is at a height of 1. That's the one point we expect you to do. So what we can do is we can look at this function and we can say, well, let's look at the function on our calculator now. So I'm going to now graph this. E to the 5x is already in there. I'm going to do a zoom 6. So that gives me a picture. Now where I want to look is I want to look near x is negative 1/2. So I'm going to adjust my window first. There's lots of ways that you can do this. I'm going to adjust my window. And I'm going to adjust the x value to fit somewhere around negative 1/2. So I'm going to go from -2 up until 1. Why did I pick that? That's just because I picked it. So now we can see there's our curve. You can see that I don't need nearly all this y space because I'm just trying to look in here. But what I want to do, I want to look at what's happening when x is negative 1/2 so that I can keep changing my window, or I can use some of my other features on the calculator. And one of the features that we've never used before is the zoom box feature. So here's at my graph. I've adjusted the window a little bit so it's a little bit closer to the x value that I want. And then I'm going to select zoom, and I'm going to select box. And it's going to give you a cursor first. So you want to take that cursor and you want to make sure you get to the left, upper left. So you want to be above the graph and you want to be to the left of whatever your x value is. So I want to be to the left of the x value and I want to be above the y value. Now when I hit enter, the cursor turns into this square, and now I can move that square left and I can move that square down, and all of a sudden I've got a box that covers that area. And when I hit enter, it'll zoom in to that part of the graph. Now look at my x value here is at negative 0.5. So I want to zoom in even more into this little area. So I'm going to go a little bit to the above and to the left. I'm going to zoom box, hit enter, and I'm going to make a box around that part of the graph. And as you notice, as I get closer and closer and closer into this picture, it still looks a little curvy here, but I can keep zooming in, and as I get closer and closer and closer, get a little bit to the left of negative 0.5, enter. Get a little bit to the right of negative 0.5, there's negative 0.49, enter. This basically looks like a line, and that's the idea of local linearity, is that when I take a curve, depending if I make my window small enough, every curve starts to look like, well, no, I shouldn't say every, but a differentiable curve will start to look like a line wherever near that point that you're trying to attack. So we zoomed in and we got a picture. Now that kind of makes sense. Look at our picture here. Does our picture have anything weird happening? No, it looks pretty smooth. And you could kind of think if you could zoom in your paper to just look somewhere over here by x equals -1/2, yeah, that looks kind of basically like a line. I know it's still a little curvy, but the more I zoom in, the less curviness I get. So now let's look at a scenario where things might not be locally linear. So this is what family of functions. Actually, I'm not even going to say anything. Sketch it. You don't need any hints. You should know how to sketch this thing by heart. All right, hopefully you notice that this is what kind of a family. This is our absolute value family. The shift is on. We're shifted forward 2 and we're shifted up 1. So shifted forward 2 and up 1. I've got a positive leading coefficient, so I'm going to have a positive absolute value graph. It's going to look something like this. So now let's do the same thing on our calculator, and we'll talk about zooming in. So I want to take absolute, that's underneath math. There's two places. You can go math and number or alpha F2. I like that one better. Absolute value, oops, I got to go into y equals first. Alpha F2. Absolute value of x minus 2, jump out of the absolute value, plus 1. I'm going to do a zoom 6, because remember, we were all zoomed in on that last graph, and so here's my picture. I want to take a look at what's happening where x is positive 2. So I'm going to go to zoom box again. I don't need to change my window because I can make a pretty good box around that spot. So zoom box, take your little cursor, and you want to get above and to the left of the point that you want in question. So I'm going to hit enter. I'm going to now make that box cover that section of the graph. I'm going to go a little bit beyond it this time. Okay, there's my picture. Now if I look here, over here is where x is -2. So I want to zoom in around this spot. So now I've got a better zoomed in picture. I'm going to do another zoom box. I'm going to get up here. I'm going to get a little bit to the side, hit enter. And I'm going to try to put a box around. And if you mess up, just hit zoom again and hit box again, and then you can just move your cursor again. So I'm going to get something that I can highlight. I'm going to get to the left, and now I'm going to get below it, and I can put it there. All right, here we go. This is, I don't think we need to keep zooming in. I think you can tell. Right around 2, so 2 is right around here. Is my graph basically a straight line? No, no. This function is not locally linear. And that makes sense because we have what's called a sharp turn. So in this case, we would say something along the lines of f prime of -1/2 exists, oops, there we go. F prime of -1/2 exists because f is locally linear at x equals -1/2. Now let's use that same logic over here, except use it in a different way. F prime, g prime of x equals dne. Dang it. G prime of 2 equals dne. That's a lot better. Why does g prime of 2 equal dne? Because f has a sharp turn at x equals 2. So we like to usually say, well, I'll just leave it at that for now. The idea is if you're locally linear, your line is basically straight, which means you basically have a tangent line, which means you can figure out the slope using the derivative formula, the derivative by definition. If you don't have a locally linear, think about the one-sided derivatives here. If I took the tangent line of this, it would be some positive. The tangent line of this would be some negative. Those are clearly not the same number. They have different slopes. So the one-sided derivatives are not equal, which means my overall derivative is not does not exist. And we call that a sharp turn. If you have a sharp turn, your function cannot be derived at that location. So here's some functions. You should be able to get in the habit of being able to look at these and just telling right away whether or not they're going to have a sharp turn. So what family is this? This is the absolute value family. So it's over for me. Well, I guess I shouldn't say that. I shouldn't say that. I'm sorry. We have to look at where we're evaluating this. So I need to make a quick sketch and get an idea of what the graph looks like before I jump to any conclusions. Because the sharp turn, I know this graph has a sharp turn. That's what I was going to say, is I know this graph has a sharp turn, but I don't know where. I'm guessing it's going to be at -3, but I don't know for sure. So I'm going to make a quick sketch. I'm going to do a little bit of work first, algebra. Before I try to sketch this, I'm going to get it into a much more convenient form. F of x equals, I'm going to factor out the 2. That's legal, considering the 2 is a positive. And now I have an absolute value function that has been shifted 3 to the left. 1, 2, 3. And it has been shifted nowhere on the y, so I don't need to shift it on the y at all. So my sketch is going to look something like that. At x equals -3, is our function locally linear? No, it's not. No, it's not. So our write-up would look something like this. F prime of -3 does not exist because f has a sharp turn at x equals -3. Okay, so let's start off. Oh, this one's a little bit tougher. We got to think a little bit harder about what this graph looks like. So I'm going to give you a second. See if you can think of what this graph is going to look like by memory. This is one of the functions I do expect you to know, by the way, just for the record. All right, how'd you do? So what I did was I thought about, okay, who is this graph kind of like? Well, if it's a cube root, it's got to be kind of like cubed. And I know cubed looks like this, right? So what I want to do is I want to take that cubed graph. I'll make a little sketch of cubed. Here's cubed. To turn f, so this is y equals x cubed. To find the inverse of that, I would take this line, and it's probably getting to the spot where it's worth starting to memorize this or catching on a little bit more when this occurs. If I want to sketch the inverse of this, I would reflect it over the line y equals x. I would flip it over the 45-degree line. So when I flip it over that line, I end up getting a curve that looks like this. There's my sketch of the cube root function. Okay, so now we don't have to use this on our calculator. We can look at the picture. Does this look differentiable at x equals 0? Yeah, it does look okay. You got to be careful, though. It does look like, okay, there's no sharp turns. But what's the other problem here? As I look at these slopes, I'm going to zoom in a little bit so I can show this a little bit better. Okay, look at the slope. Okay, there's the slope. There's a slope. There's a slope. What's happening to my slopes as I get closer and closer to actually 0? My slopes are approaching vertical. My tangent lines are approaching verticalness, which means my slope is approaching undefined. So a little bit sneaky there, a little bit sneaky. We would say f prime of 0 equals dne because f has a vertical tangent line at x equals 0. And this might seem a little bit like, wait, how am I going to remember? We're going to do a lot of examples, or at least we have an opportunity to do a lot of examples of these in the homework sets, okay? And this is where you're going to get a chance to try to look for. So right now, what do we have as some problems? What are some reasons why my derivative would not exist? One reason is I've got a sharp turn. Another reason is I've got this vertical tangent line. Those are two situations for which my derivative would not exist. Let's see. Let's see how you do sketching. Well, you wouldn't know how to sketch this one yet. This is one worth memorizing. The graph of x squared cube rooted. I don't really have a great answer for this, why it looks the way that it does. I mean, the best I can tell you, think about it this way. You have, remember that this is the same as saying f of x equals the cube root of x getting squared. You buy that? Remember that the bottom of the rational exponent becomes the root, and then the top becomes the power. So if I take the cube root graph, which we just graphed over here, and I take all those y values and I square them, what kind of y values are these? These are positive. So when I square these positive y values, I'm going to get more positive y values. So it's going to look something like this. Maybe a little bit taller because these numbers are getting multiplied by themselves, which usually means they're going to grow. That's okay. Now look at the other side though. What kind of y values are these? These are negative y values. So if I take these negative y values and I square them, the other side of the graph is going to look like this. This is a graph worth memorizing. X to the 2/3 looks something like this. This graph is worth memorizing. You'll see it pop up every once in a while. It is worth memorizing. All right, so we're going to zoom in. We're going to zoom in around x equals 0. So as I look at x equals 0, if you zoomed into that area, would this be locally linear? No, it wouldn't be locally linear. Right? We've got what situation again? We've got a sharp turn. Now this sharp turn has another name. You might see it called a cusp, but I'm okay with just calling it a sharp turn. So f prime of 0 equals dne because f has a sharp turn, and this time I'm going to put in parentheses cusp at x equals 0. So what's the difference between a sharp turn and a cusp? Well, all cusps are sharp turns. So if you just remember calling them a sharp turn, you're fine. A cusp is this specific one where they kind of come in at a point. I don't know how to describe it. Never mind. I'm not going to try to describe a cusp. I would not use the phrase cusp. I don't use it. I used to use it a lot because I thought it was a cool word, but the reality is it's not. It's tough to explain the difference between when it is a cusp and this is not a cusp. At least I don't think it is. Make a sketch. Rewrite this function. Rewrite this function in a way that's going to be helpful for you to sketch it. I'm going to give you a second. Try to think about how you can rewrite this so that you know what family it is. So you know basically what the graph is going to look like. You now need to understand what transformations applied. Well, the first thing I would do is I would flip these around. I wouldn't like the x. So I'm going to take the negative x, I'm going to put it out in front of the 10. The next thing I'm going to think about is, well, I'm not supposed to have a negative in front of this, so I'm going to factor that negative out. So I'm going to take out a negative. That's going to leave behind x subtract 10. And now we can start to really talk about the transformations of this function. What does this thing do? Well, it's inside with x. So negatives always cause reflections, but since it's inside with x, this is going to be a horizontal reflection. And then this piece right here, this is old news. That's a number added onto x, so that is going to be a shift in the x direction. And what do we got to remember when we shift in the x direction? It always does the opposite of what you'd think it would do. So let's make a sketch. So my graph is going to shift forward 10. I'm not going to draw 10 tick marks, so you're just going to have to take our word for it that over here is 10. It doesn't shift anywhere on the y, so this is my, I don't think it's called a vertex for a square root. I don't know what that's called. The square root graph normally goes forward like this, but we have a horizontal reflection, so it's now going to go backwards like this. Okay, so what's happening now at x equals 10? So I'm going to get out my marker, and I'm going to kind of highlight what's happening over here at x equals 10. Okay, well, we don't have a problem here with the, we don't have a sharp turn, right? We have a bigger problem. There's nothing on the other side of 10. Our graph just stops here. So what's the derivative from one side? The derivative from one side, maybe we could figure out what that is. But remember, for you to have a derivative that exists, your one-sided derivatives have to equal each other. So your derivative from the left and your derivative from the right have to be equal. And clearly, this graph doesn't even have a derivative from the right side. So our function, again, is not differentiable at that location. So f of 10, f prime of 10 equals dne, because f is not differentiable from both sides at x equals 10. Now, this stuff is kind of the big picture stuff. It's one of those things that you don't have to usually prove a whole heck of a lot. It's just introducing to you some of the visual scenarios for which you know a function's derivative will not exist. So if I have a sharp turn, or if I have a sharp turn that kind of has this kind of curviness to it, which I think is called a cusp, we could look that up later, or you could look that up on your own. We have a vertical tangent line. So my slopes end up becoming vertical, which then I don't have a derivative for that because a vertical line has a slope that's undefined. And then the fourth scenario is when we have a graph that doesn't have a derivative from both sides. I'm curious about what a cusp. Let's see if we can look up cusp. What is a cult? What is a cusp in calculus? A cusp, or spinoid, is a point where two branches of the curve meet and the tangents of each branch are equal. A corner is more generally when where the two branches of the curve meet and the tangents of each branch are equal. That doesn't help me much. I'm still confused because this tangent, I guess those two would have the same tangent line, wouldn't they? If you drew the tangent line from this side and the tangent line from this side, I guess it would have. I guess so. I don't have a good way to explain it, so I'm not gonna talk about cusps. I'm gonna keep talking about them as just sharp turns. All right, now we get to the big stuff. This is the stuff. These things are kind of nice. You're gonna see pictures. You really don't have to prove these very often. Like I said, these are just kind of pictures that you can think of to visualize whether a function is differentiable. This is something that you're going to use a lot. Very important theorem. If f is differentiable at x equals c, then f is continuous. That's huge. So if you tell me that the function is differentiable at c, at x equals c, then it automatically is continuous. So if I get a problem, and they'll do this all the time, is they'll give you a problem that says f is differentiable, is everywhere differentiable. They'll say that phrase, everywhere differentiable, which means every point has a derivative. Well, that also means, without them saying it, that f is continuous at every single point. And then remember from your geometry days, contrapositive. It doesn't, so what if f is not differentiable? Then f is, no. If f is not differentiable, then f is not continuous. I can show you a counter example really quick. So here's a counter example. F is not differentiable. Therefore, f is not continuous. That's false. That's not true. Here's a picture. My function goes like that. Here is f differentiable. No, f is not differentiable because we have a sharp turn. But is f continuous? Yes. So this is not true. That is not, that's what we call maybe the inverse or the no, this is the contrapositive. Anyway, the contrapositive says the reverse though. If f is not continuous, then it's automatically not differentiable. So in a minute here, we're going to prove whether a function is differentiable. To do that, we have to prove if it's continuous first. And so if you prove that the function isn't continuous, you could stop. The game is over because if you're not continuous, then you're not differentiable. Let me show you what I'm talking about. So here's our function. Determine f of x is differentiable at x equals 1 by using the alternate form and then a continuity argument. So let's do the alternate form first. What's the alternate form? I have no idea. Like I said, I don't memorize all this stuff. I just use, what's the alternate form? The alternate form is this one. That's where they actually plug it in. I'm not going to do it that way. I'm going to do it by definition. By definition. Okay, so by definition means I want to first figure out what's the limit as we approach, what's the limit of my function, what's the limit of the derivative of my function as we approach from the left. So I need to figure out sorry, I was just thinking, I'm thinking about how I want to explain this. I'm gonna see if we can cut to the chase here. I haven't shown you this shortcut yet, but let's think about this for a minute. If this is my function on this side, what do we know about the tangent? The tangent equals the derivative. I should have said the derivative equals the tangent. I don't like that I did this. But what is the derivative equal of the tangent? The slope. So what's the slope of something simple like this? 2. Right? That's in y equals mx plus b form. If this doesn't make sense, don't worry. I'll fix it later on. But for now, I don't want to go through the whole process of doing the derivative by definition here. And I don't think you want to watch me do that again. So the derivative is equal to the slope. I'm just going to get rid of that word tangent. The derivative is equal to the slope. And what's the slope here? 2. So if we were to write this up properly, we would say the limit of f prime of x as x approaches -1 from the left, and the limit of f prime of x as x approaches -1 from the right. All right, what are those equal? What's the derivative of my function on the left side? Well, the left side of -1 would be this function, whose slope is always 2, so the derivative has to be 2. The derivative from the right would be the slope of this function, which turns out to be 2. So what does that mean? Therefore, that my derivative, f prime at -1 equals 2. No, this is false. Wait a minute. if the one side limits equal the same thing, then that's the derivative, right? No, not quite. You first have to prove continuity. Or maybe I shouldn't write false. Maybe I should write false. Instead of that, maybe I should write not necessarily. So we've shown that the graph coming in from one side is at a height of 2, or the slope is at a slope of 2. Coming in from the other side, I've got a graph that has a slope of 2. Life is good. My slopes meet up. They don't actually meet up because my function isn't even continuous there. Let's go back and try to prove continuity. So over here, this is what we call, where would be a good color to highlight here? This is what we call proving differentiability. I never want to write out that whole word. Proving differentiability is I look at the derivative from one side, I look at the derivative from the other side. If they're equal, you're proving that you're differentiable. In parentheses, if continuous. If continuous. So you have to first show that your function is continuous. You can't be differentiable if you aren't continuous. That was that theorem that we just talked about. So I'm going to try to prove continuity. Prove continuity. What are the 3 things we have to prove with continuity? Number 1, that the point exists. So f of negative 1 equals, yep, I can plug it in here. Negative 1, 2 times negative 1, negative 1. Negative 1 minus 1 is negative 2. No, let me try again. 2 times negative 1 is negative 2, minus another 1 is negative 3. How about that? That's better. Then I need to prove what? I need to prove that the one-sided limits are equal. So the limit of f of x as x approaches negative 1 from the left equals, so I put negative 1 in here. Negative 1 is negative 2. Negative 2 minus 1 is negative 3. The limit of f of x as x approaches negative 1 from the right, I put negative 1 in there, I get negative 2. Negative 2 plus 1 is negative 1. What does this mean? These two things come together to show us, therefore, the limit of f of x as x approaches negative 1 equals what? dne. So our function is not continuous. We have a point, we have one-sided limits, but the one-sided limits are not equal. So then our write-up would look something like this, where we would say since f is not continuous at x equals negative 1, then f is not differentiable at x equals negative 1. Now you might say, well, wait a minute, didn't we just prove differentiability? Didn't we just show that these two things are at the same height? Well, let's sketch it, or let me see if I can get a good graph here and show you what happened. So we would do 2x minus 1 divided by x is less than or equal to negative 1. And then I'm going to graph 2x plus 1 divided by x is greater than negative 1. Oops, dang it. Is greater than negative 1. I'm going to do a zoom 6 just to give me a good window going here. And then I'm going to now try to get a good, what would that be, like negative 3 to 0. Do these two lines have the same slope? Absolutely, right? Let me make a better window and see if I can get this a little clearer. Negative 2 to 1. Do these two lines have the same slope? Sure they do. Sure they do. I believe that. As I can look at it, it does look like they have the exact same slope. The problem is, yeah, the derivative from here is 2, the derivative from here is 2, but they don't meet. How can you have a derivative if your 2 points don't meet? If they don't even meet, they can't be differentiable at that spot. So that's the big idea there. Okay, so symmetric form, the numeric value, oh boy, here you go. Feel free to, another one that I don't ever see. I just never see it appear very often. There's probably going to be a couple in the homework like this, but we can talk about those in class. Now, what's really nice is on the calculators, there are times when you can use your calculator and you got to find the derivative. Don't bother with doing the derivative the long way when you can use your calculator. There's 2 ways that I'm going to show you how to be able to do this. So the first way is to quit out of here. I'm going to do this F2 again. It's also underneath math. Math, and then you go, keep going down until you see, there it is, n derivative. It's going to bring this up, and I'll show you how to fill this in. Or you go alpha F2, this is the one I like to use, and then function integrate. Fn integrate, function integrate. No, dang it, I don't want to integrate, I want to derive. So n derivative. I want to take the derivative. Okay, d dx, that's always going to be an x, and then you're going to put your equation in here. 3 minus 6 absolute x plus 1. And where do we want to derive this? We want to derive this at -2. So that's the coding, that's the keystrokes that you're going to use to plug this in. It's always d dx, then you put in your equation, you don't need the y equals, and then you say where you want to derive this. You hit enter, it spits back 6. So we can now say that f prime of -2 is equal to 6. We can do this again, hit enter. I'm going to go back, and now I'm going to change this to a 0, and I get -6. So the derivative at 0 is -6. Now you can also do this graphically. So if you know that you're going to find the derivative at a lot of different places, I can go here. I'm going to clear out my old stuff. I'm going to put in my equation. 3 minus 6 absolute x plus 1. Zoom 6 to give myself a decent window. Okay, that's good enough. Everything good on your calculator for graphing is underneath calc. So when I go second calc, you'll see right there, I've got dy dx. I can select that, and now I can just type in the x value that I want. So if I want my x to be -2, I type in -2, and it spits back that the slope of the tangent line, which is nice because the tangent line is just this line right here. The slope of that line is 6. The derivative there is 6. When I go second calc, I go down to dy dx again. Remember, that's another way to say derivative. Now I'm going to just type in 0. That finds me the derivative at 0 is -6. Now you got to be a little bit careful. Your calculator sometimes will give you a flaw, and that's why I like to use the graph to do this. Your calculator will sometimes say that the derivative exists even when it doesn't. So I'm going to do dy dx. I'm going to now figure out what's happening at -1. It says that the derivative is 0. That is false. What do we have going on here? We have a sharp turn at x equals 1, right? Look at your family. This is an absolute family that's been shifted back 1, so the sharp turn is occurring at x equals -1. So you do have to be a little bit careful. Your calculator's answers on 13C are wrong. Your calculator is programmed to use this formula, and so what it does is it just took the average of these two slopes and went that way. Well, that's a problem when you've got a sharp turn. So this equals dne with a sharp turn, even though my calc gave me an answer. You know, every once in a while our calc does let us down. You've got to be careful. You've got to know better than what your calc is saying. Do you remember when we did this in pre-calc? where sometimes we did, we tried to figure out the min or the max, and it would give us a number like 1.000000147, something like that. And we had to know that our calc does a pretty good job most of the time, but not always. So we got to be a little bit careful. All right, so hey, this is your chance. Get into that homework, dig into that, bring a lot of questions to class, and let's not wait to the last minute to try to figure all this stuff out, because that generally does not go very well. Good luck.